let's try the same thing with the function f2 of x equals 1 divided by x squared. And again, I have my formula here that is calculating the integral for me. And I have the blue region filling in, actually showing the area that the integral measures. Integrals measure area. So just like before, I can move my B slider and say I want all of the area between 1 and 2, bounded by this function and the x-axis. And Desmos has calculated out that that area will be 0.5, so just a half. I can take a larger value of b, maybe b equals 4. Now I'm getting integral equals 3/4. And I can keep moving my slider outward. I'll zoom out a bit so you can see the function here. So as I move this out, I have filled in more of the area blue. So between 1 and 10, there is 0.9 units of area. Between 1 and 103, there's 0.99 units of area. Between 1 and 276, there are 0.996 units of area. So it's getting bigger, but it is slowing down in a way that we did not see with the function 1 divided by x. So if I continue, I claim I'm never going to get a value larger than 1. And you can see here, when I get out to b equals 1,000, the value of this integral, I have 0.999 units of area shaded blue here. So this integral looks like it is approaching some limit if I were to integrate across the whole x-axis. But I cannot use the fundamental theorem of calculus if I'm going to do this. FTC requires me to say, find an antiderivative, take the difference, evaluating at B and at A. But infinity is not a real number. So I'm going to be stuck unless I approach this in a proper methodical way. So the first part of these lectures from section 6.6 are the method of actually treating limits of integrals in a sensible way to get an answer that'll be, an actual useful number.